Alright, taking a look here at exam 3, which was unit 3 from 2015. Alright, the first couple set of questions was nomenclature. You need to be able to do dienes, so 2 alkenes, so a diene. Need to know something about E and Z, obviously. It's kind of a basic alkene question with substituents, but of course an ene, finding the longest parent chain with the alkene in it. Next over here, doing a little E and Z with the alkene again, given the structure, but then having to write the name. Again, long have the longest parent chain with the alkene in it. Finally, a ring with an alkene. Again, the parent chain being the ring containing the alkene. Going from there, naming the substituents. Number 2, kind of looking at these things and being able to identify what they are to each other. So in this case, these two are identical. These two are identical. Be careful. You got to do the R and S here. So we flipped around these things. You got to do the R and S. Again, two things are identical. Here, diastereomers, of course, meaning one stereocenter is the same and one. So here, one stereocenter is the same, one is different. So those are diastereomers. Using some Fisher projections, these are mirror images. These are enantiomers. Of course, you could figure out R and S as well. And finally, some constitutional isomers, which actually have different constitutions, different actually connectivity of the bonds. So here, looking for star all the asymmetric centers. So no asymmetric center here because these are both 1, 2, 3 propyl groups. So that's not an asymmetric center. There's 1, 2 there, 1, 3, so 4 total. Assign the R and S. Do the rankings. You know how to do that. Assign E or Z for alkenes. E or Z for alkenes. Got to do that. And circling meso, so something with an asymmetric center, asymmetric centers, and a mirror plane, and that would be this molecule would be meso. So the molecule is chiral, but the molecule is achiral, meso, even though it has asymmetric centers. Meso is achiral with asymmetric centers, so a mirror plane, even though it has asymmetric centers. The question here about ring strain and carbocations. So having to understand a carbocation is, of course, sp2 hybridized, so it has bond angles of 120. So that would not jive well with a 4-membered ring. Square with 90-degree bond angles, but it'd be even worse with a cyclopropane carbocation, the 60-degree bond angles. So worst for ring strain, second worst, and then tertiary versus secondary. So it's about hyperconjugation between these two. This has 9 hyperconjugation buddies, so it has 9 things 2 sigma bonds away that can help stabilize that. So that'd be the highest energy. That'd be the lowest. That'd be the most stable. Why? Right, more substituted, then more hyperconjugation, and then of course less angle strain. Right, that idea about the sp2 hybridizes the bond angle is 120 versus 90 or 60, so that'd be the worst. Here, this question say give the mechanism for the first step, right? Only the reaction below show the final product as well. What type of addition is this? It's a cis addition, so it's BH3 to the empty p orbital with boron. The boron wants to go to the left substituted carbon, and it's going to add syn. Shown here, so I'm showing one way it adds. And then, of course, the second step is just replacing the OH, right? It'll also add on the other side, but I didn't ask to show that here as well. Give 3 factors that affect the rate. Of course, here's our fishing example. You need to have a lot of fish, so concentration affects the rate. You need to have sufficient energy. The fish need to run into that hook. But that's not it, not just enough. They also have to run into the hook in the correct way to actually be hooked, so orientation matters as well. So concentration, sufficient energy, and orientation of the reacting molecules are the 3 things that affect the rate of reactions. Here, provide a detailed mechanism for the following reaction to form a major product. Be sure to draw all intermediates with proper formal charges. So the first step, nucleophile, is that pi bond, attacks the hydrogen. We're going to form a carbocation, carbon 2, because that's the more substituted carbocation. So that'd be more hyperconjugation to make a CH bond there. We actually have an alkyl shift, so we have 3 ethyl groups, so they're all the same. So one of them moves over, so it's an alkyl shift, a 1,2 shift. So carbon 4 here is a nucleophile. Carbon 2 is the electrophile. So when that happens, now the carbocation is now on carbon 3, which of course now would be a tertiary carbocation, so it's more stable. That's why it took place, because this was secondary and it goes to tertiary. Also of note, Cl- is in here to help balance our charge. But again, here to think about Cl-, of course, along for the ride, but now we have a solvent. The solvent, of course, is in much higher concentration than the Cl-, because of course, as before, concentration affects rate. So the ethanol here is going to attack the carbocation, so nucleophile is the lone pair on the oxygen. The carbon 3 is the electrophile. The only thing that moves is there's no bond that breaks to oxygen. The hydrogen and this carbon stay attached, so make sure they stay attached. So make another intermediate, which has a plus charge on the oxygen. Now you can use the chlorine to take that H, or you can just have the H fall off, and you have H plus and Cl minus, and you get the final ether product. So again, here you have one intermediate, two, three intermediates with 1, 2, 3, 4 arrows, which means you'd have to have 4 transition states because you have 4 mechanism arrows. So 4 transition states with 3 intermediates, A, B, and C. So the dry ion free energy diagram, the highest energy intermediate will be the secondary carbocation. But now a tertiary carbocation would be a lower energy, right, because it has more hyperconjugation buddies. But the transition state for the first one would be the highest. That'd be the rate determining step. Now intermediate C is much more stable because everything has a full octet. Both A and B, things don't have a full octet. So this would actually be much lower in energy than either A or B. And the final step is just that hydrogen falling off to H plus, or the chlorine taking it and making HCl. And that's our final product. And the starting material and the final product, we're not sure which one's higher in energy or lower. That's not really a big deal here. So number 10, for the reaction below, draw sigma and sigma star orbitals for a carbon-bromine bond in the starting materials. Describe why the stereochemistry changed from S to R in the reaction. So we're giving you the product, so S to R. The reason why it changed is because sigma star is 180 degrees away from this carbon-bromine bond. So the sigma bond orbital, the electrons are by the bromine. The antibonding orbital, sigma star, the electrons are behind, more by the carbon, but it's 180 degrees away. So when this lone pair attacks sigma star, bromine gets kicked out, but it inverts and it switches the stereochemistry. So stereochemistry inverts because the antibonding sigma star orbital is 180 degrees from sigma bond. So a nucleophile attacks from the opposite side, creating the other enantiomer. Alright, for number 11, it said add mechanism arrows and formal charges to the reaction below. So this is very similar to a workshop we did. So here you do bonds broken, bonds formed. This lone pair in the oxygen is going to come attack and kick out the chlorine to make Cl minus and actually have the plus charge to add in those charges. Here, the D ends up on this carbon here, so and this pi bond is formed, so the electrons have to come down. This pi bond attacks that D, and those electrons go there, so 3 arrows. So the deuterium ends up there, regenerate water, so we need to break the DO bond. We also need to break the pi bond and form a new pi bond, so those arrows will do that. Here for this one, the carbon-carbon bond is formed, and this carbon-chlorine bond is broken, so those electrons come here, and they have to come from the back side, of course. And notice how they're anti to each other. And as this electrons go there, that kicks out the chlorine, and it breaks that carbon-chlorine bond, and you get this anti-trans product. So this is a very important to do. Bonds broken, bonds formed. Just be like comfortable moving electrons and using the arrows to do that. And also balancing our charges. So here for some reactions. For each of the following reactions, provide either the reagents or the starting materials. So for this one, we want to think this is an ozonylysis. So what were carbonyls? We're coming together to form alkenes. So numbering is very important here. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So 3 and 6 actually need to form a new pi bond. So I put that pi bond there, and then this number accordingly out. So it'll be a 1, 2, 3, 4 four-membered ring. It might look weird, but that's the way we need to go backwards to work from there. For this one, we start with an alkene. It looks like we added 2 hydrogens. So the way to add 2 hydrogens is H2 with palladium on carbon, that catalyst, palladium or platinum. So H2 and that catalyst are the keys there. Here, you can see we have BH3 and OH minus, or H2O2. And it looks like the H and the OH have added syn. And it looks like the OH ends up on the less substituted carbon. So what alkene did that come from? Well, the 6 and 5 are on the same side. They're hatched. And 2 and this H are on the same side, so they'd be on the same side in the alkene as well. So it's that correct E alkene is the key here. So number 13 here, for each of the following reactions, provide the products, draw possible products, including stereochemical relationships to each other. So here we have Br2 in water. So again, we have some regioselectivity here and some stereoselectivity. So the bromonium ion is going to form, and the water eventually is going to attack the carbon that's more substituted, which is this one here. And since the bromonium ion can form both at the top and the bottom, we have a bromine up and an OH down, and an OH up and a bromine down, so you're creating enantiomers. For full mechanistic detail, be sure to go back and look at your notes for how Br2 adds, and especially with water. Here again with HBr, we're going to attack, we're going to form a carbocation, the most substituted carbon, and once we form a carbocation, we can attack a carbocation from the top or the bottom, so we both get both R and S for this site, but notice we already started with the chiral center. So if we start with the chiral center, this one never changes, whereas this one you get both products because of the carbocation. So actually, in this case, it's a little tricky even beyond that. If you look, we actually didn't create a chiral center. It's actually symmetrical, so these are actually identical. So not actually making any stereocenters here, so a really tricky, tough one here. These are identical.